time for us to take it to the limit. We're going to be doing practice with problems involving multivariable limits. As with all parts of mathematics, the more practice you do, the better it is to spot patterns and see, oh, in this situation I can try this, in this situation I can try that. So do as many problems as you can on your own. If you're following along with the video, make use of the pause button. Pause me if you see a problem you like and try it yourself first. And then if you need to see the answer, go ahead and unpause me and we can compare and we'll see how we do. Well, let's begin. So for our first problem, nice warm-up. Determine the limit as x and y goes to 0, 0. We're going to see a lot of limits like that. And the expression is x to the fourth minus y to the fourth over x squared plus y squared. Now, one of the things you should always think of is what's happening at 0, 0. Because maybe nothing bad happens at 0, 0 and we're done. Well, probably something interesting is happening. So what do? Well, if we plug in 0, 0, what do you see? You get 0 to the fourth minus 0 to the fourth upstairs. Downstairs, you get 0 squared plus 0 squared, which is 0. So we're going to 0 over 0. Aha! That means more work. More work. So when we see something like 0 over 0, we know more work lies ahead. Well, maybe not too bad. I mean, it is, after all, our first problem. So maybe if we think about it and say, is there some way we can rewrite it, or is there some way to understand it? And we say, hey, wait a second. X to the fourth minus y to the fourth, that's not just anything. That's the difference of squares. See, difference of squares, that's something that we see so often. We want to almost be trained to see, oh, I see a minus. Do I see two things which are squared? If they are, aha, we're going to go for it. So in our case, we say, well, wait a second. You see, we really could write this as limit as xy goes to 0, 0. And what are the squares? It's x squared squared minus y squared squared over x squared plus y squared. Well, that's really the same. Limit as xy goes to 0, 0. See, this is a squared minus b squared. So it would be a minus b, a plus b. All right. Well, why is that good? Well, what do you see? You see an x squared plus y squared in the numerator. You see an x squared plus y squared in the denominator. And we say, perfect. They cancel. Because when we are away from 0, 0, which is what we're doing, when we're talking about a limit as we go to 0, 0, we're never at 0, 0. We're saying we're near there. And so away from 0, 0, x squared plus y squared, no problem. And so we can cancel them. Whoosh, and they're gone. And so we say, hey, this is really the limit as xy goes to 0, 0 of x squared minus y squared. Well, now we, again, plug it in. And if we get something that makes sense, we're done. Well, if you plug it in, you get 0 minus 0, and therefore our answer is 0. And we're done. Wow. Cool. I hope all our problems are this much fun. Well, probably they'll be more interesting, I suspect. But I definitely hope they'll be fun. Okay, so let's try another one. Find the limit as we go to 0, 0 again, xy over x squared plus y squared. Now, well, there's no factoring to be done here. Think about, okay, what's happening? In some sense, we can say, well, it's almost like the same degree on the top as it is on the bottom, right? They're both kind of like squares because we got, x times y, that's like degree 2, right? X times another, something that's kind of like an x. And so when we see it's like, oh, they're kind of about the same degree, it makes us kind of like, something interesting might be going on. Now, if you don't know anything, what you should do is ask yourself some questions such as, well, let's look at some approaches. So, for instance, here, we could say, let's look at how we can get to the origin, and we'll do it in a few different ways. So suppose we approach from left and right. Now, what do we mean by saying we're approaching from our sides? What we really mean is we're going to say, look, we're going to fix y to be 0 and just look at the limit as x goes to 0. So, in other words, from the sides, we can change it from being a limit involving two things changing, two variables, if you will, to one variable. So this would become a limit as x0 goes to 0, 0. Or you really can just replace that as just saying x goes to 0, right? Because that's the only thing that's changing. So as x goes to 0, and now we know y is 0. So what do we have? We're going to have x times 0 over x squared plus 0 squared. Well, that's really, look, the same as the limit as x goes to 0 of 0, which is 0. So as we come in from the sides, it's looking suspiciously like 0. All right, well, let's come from a different direction. Well, how about we come from top and bottom, above and below? So what's happening there? Well, if we're coming from above and below, now it's like we're saying let's let x be 0 and y can vary. So what do we do? A similar process, right? We can say, look, let's look at the limit here. 0y goes to 0, 0. See, the key thing is we're going to change from a limit where we have two things varying to where we have one thing varying. And again, we can say, really, hey, that's just the same as y goes to 0. And what do we get? Well, we're going to have something similar. 0 times y over 0 squared plus y squared. But it's the limit as x goes to 0 of 0, which is 0. Okay, so we now know from top and down, we're going to 0. Left and right, we're going to 0. And you're probably thinking, okay, the answer is 0, right? No, because there's all these other directions. What we have said, though, and what we can say definitively at this point, is if there is a limit, it must be 0. But it still might be that there is no limit. Okay, so let's try at least one more direction. Well, let's come in at a nice line. How about we come in along the line y equals x? Now, how do we do this? In general, if you want to come along any curve, one way to do it is to think about moving in on a parameterized curve. So I can think of this as being t comma t. That's how you parameterize the line y equals x. And then if I want to go to 0, 0, I can say, look, as t goes to 0. So I'll look at the limit, and this is along the line y equals x, which again, t comma t is the parameterization. And I'll take the limit as t goes to 0 of upstairs. I'm going to replace x by t and y by t. So it'll be t times t. Downstairs, t squared plus t squared. Well, that's the limit as t goes to 0. T squared over t squared plus t squared, also known as a half, which is a half. And now we're like, oh, well, that's very unusual. Because what? Now we're saying, look, before we thought we were getting 0, and now we're getting a half. Well, what does that mean? When these don't match, then what we can say is, look, limit does not exist. Because in order for the limit to exist, you always have to have a consistent answer regardless of which way you approach. And so we've now said, hey, if we approach along this line y equals x, we get a different answer than if we approach along an axis, and therefore the limit does not exist. Okay, good. This is going to be a fun way to, if you have a problem where the limits do not exist, because it's sort of like, how do you find the right way to approach? Well, you have to probe a little bit. Sometimes not so obvious, not so obvious. All right, well, let's try another one. All right. Determine our limit as xy goes to 0, 0 of x sine x over x squared plus y to the fourth. Okay, what can we do? Well, let's go along our axes again and see what we get. So I always think, when in doubt, if you don't know anything, see what's happening along the axes. And that can oftentimes be a good place to start. So we mark it. We're heading towards the origin. So we're heading to right there. And what are we going to do? Well, let's go from up down first. Because here, this is really just along the line x equals 0. So it becomes just simply the limit as y goes to 0. When we plug in x equals 0, we're going to get 0 sine of 0 over 0 squared plus y to the fourth. Well, that simplifies a lot. So that becomes the limit as y goes to 0 of 0, which is 0. Great, good. Now, at this point, we don't know what our limit is, but we know if it does exist, it's 0. So we've narrowed it down to two possibilities, 0 or does not exist. So at this point, it's like, okay, good, 50-50, it's one of those two. Well, let's try another direction. So let's move in along our axes from left to right. Okay, now here, this is y equals 0. So what will we have? Well, it'll be the limit as x goes to 0 of x sine of x divided by x squared plus 0 to the fourth. Well, that's our limit as x goes to 0 of sine of x over x. Now, what is that? Oh, this is a good one. We should know this limit. It's a very important one. Do you remember it? Yeah. Now, you may not remember it, but you might say, could we do a little L'Hopital? You can do L'Hopital here. L'Hopital is okay. So if you forgot, you can say, look, do L'Hopital. Now, you might say, well, wait, are we allowed to do L'Hopital? And that's actually a great question. If we're doing a limit where there's just one variable involved, yes, L'Hopital is allowed. If there's two or more, no, L'Hopital cannot be done. No. So, if you're down to a single variable, yes, L'Hopital is fine. Otherwise, you just have to go, find some other way. So, in case you did forget, you could have done L'Hopital, and you'd say, okay, do it to the top, over do it to the bottom. You're like, oh, yeah, now I remember, it's 1. But what's the key? We're like, whoa, wait a second. Compare your answers. And what do you see? Well, at one point we got 0. Another time we got 1. And these don't match. And so as soon as you have two different ones which don't match, that says, look, in one direction I think I should get 1. In a different direction I think I should get 0. Well, look, 1 and 0 are not the same. So that tells us our limit does not exist. All right, good. Well, let's try some more. Okay, now, a fun one. Oh, yeah, this will be good. So, find the limit as we go xy to 0, 0 of x squared y over x to the fourth plus y squared. Wow. Okay, cool. Well, let's do what we did before, right? Let's take it along some various lines. Okay, so let's try things. Well, let's go along the y-axis. So if we're on the y-axis, that really says x equals 0. So we're going to have our limit as y goes to 0, because x is 0, so only the y part varies. And in the numerator, well, we're going to have 0, and downstairs, 0 plus y squared. So that's our limit as y goes to 0 of 0, which is 0. Okay, great, perfect. So, goes to 0. All right, x-axis. All right, let's do that one next. Okay, x-axis. What do we have? Well, if we're on the x-axis, we can say the following. That's really the same as saying y equals 0. So that's our limit as x goes to 0. Now, because y equals 0, the numerator is 0. Then it's divided by x to the fourth plus y squared. Well, look, it doesn't matter what you plug in, right? In other words, whoops, I should have had a 0 squared there. Doesn't matter what your x is, you're still going to get a 0. So then we get 0. Wow, cool. 0, 0. All right. What about a line? Now I'm going to save ourselves some work, and I'm just going to do all the lines simultaneously. And you're probably thinking, wow, Steve, that's a lot of lines. Yes, but we want to just cut to the chase because I think something cool might be happening here. So how are we going to do all the lines simultaneously? So we're going to do along the line y equals kx. So essentially what that is if you were to graph, what's happening is we're saying we're going to come along through the origin and the slope is k. But I'm not saying what k is. So k right now could be any value, positive or negative. So y equals x, y equals minus x, y equals 0x, y equals 100x, pretty steep. Any value for k you want. Okay, so what can we do? Well, if we think about, we have x, we could say y is kx. So we could say, well, let's think of it as the limit as x goes to 0, and I'm going to have x be x and y be kx. So it would be x squared times k times x divided by x to the fourth plus k times x squared. Okay. All right. Well, now what? Well, what does this become? That's our limit as x goes to 0. There's a lot of x's in. So let's pull out all the x's that we can. It looks like there's at least 2 x's on every term. So I'm going to cancel an x squared off of every term. So we're going to get k times x divided by x squared plus k. Now, what happens? Well, as x goes to 0, well, there's a couple things. What if k equals 0? Well, if k equals 0, you might say we have some weird thing going on. But we actually have handled that case before, right? Because if k equals 0, that's y equals 0. So we can actually specify, let's say k is not 0. Because otherwise we're back to y equals 0. Okay, so here's the thing. Now just send x to 0. What do you get? You get k times 0 over 0 plus k, which means you're okay. Because you're not dividing by 0, you go to 0. Now, what have we done? Oh, this should be great, right? Because we've now said it doesn't matter which straight line you use to approach the origin. It doesn't matter at all. As long as you approach the origin from a straight line, you're going to go to 0. So we are getting 0 in all of these directions and many, many more, infinitely many directions. As long as we head towards 0 on a straight line, we're always getting 0. So by this point, you're like, okay, we're done. The answer must be 0. But no, we're not done. What's the problem? Okay, so here's where things get interesting. Remember, I used a word there very carefully. I said straight line. But we don't have to approach things in a straight line. We can approach something in any curve we want. So even though you've shown in infinitely many directions, we still get a consistent answer of 0, does not mean that the answer is 0. So at this point, you're probably saying, okay, so should we switch gears? If you've come to a point where you think that, well, maybe the limit is 0, then you kind of have to abandon this approach. Because this can only be useful if you think the limit doesn't exist. But I want to try something before we completely give up. I suspect something curious is going on here. Let's stare at this for a little bit. And I'm going to propose we don't move along a straight line. So we move along some other path. Now the key question we have to ask is, which path? Because there are so many. There are so many possibilities. So let's stare at our denominator for a second. See, in our denominator, we have this expression, x to the fourth plus y squared. What I'd like to do is find a nice path where I can basically make them the same. So, is there some path that can combine? That's what I'm after. They might say, why would you want to do that? Well, oftentimes, one of the things that makes problems a lot easier is if we can get rid of addition, especially things like addition in the denominator or addition underneath square roots. Anytime we can get rid of addition, oftentimes we can make progress. So we're looking at this and saying, okay, what would we want? Well, we want y squared to be the same as x to the fourth. That would do it. Okay, so what function when we square it looks like x to the fourth? And then we say, aha, idea. Let's choose y equal x squared. What happens? Well, notice what will happen is you'll have x to the fourth and x squared squared, which is x to the fourth, which means you can put them together into a single term. You get rid of the plus. So let's do that whole thing. Okay, so here we go. If we're going along y equals x squared, we're going to have the following. We'll think of x as being the part that varies. So it'll become our limit as x goes to 0. Now, by the way, if you want, you can use the parameterized curve. You can think of it as t comma t squared if you prefer. There's lots of ways to do this. So I'm just thinking of x as being the part which varies. But if you prefer parameterized curves, that's great too. So we're going to have x squared y, so remember y is x squared, divided by x to the fourth plus y squared. Well, that's our limit as x goes to 0 of x to the fourth divided by x to the fourth plus x to the fourth. Oh, do you see it? Do you see it? It's 2x to the fourth downstairs, which makes this the limit as x goes to 0 of a half, which is a half. What? This is crazy. Because what are we seeing here? Well, first off, let's just jump to the punchline. 0 and a half, it turns out, not the same. So, limit does not exist. But the really crazy thing is, it says, look, even though whenever we approach from a straight line, we always kept getting 0. But when we approached along this other curve, we got something which wasn't 0. This is why it's important to say, just because you've gone 0 many, many, many times, or some other value, doesn't have to be 0, doesn't mean you're done. Because weird things can happen. And it all boils down to the fact that in multivariables, you have this extra freedom to move around. And that extra freedom, well, That's what allows the strange things to happen. So, again, traveling along not a straight line, but a parabola. That's what did it. That's what tipped us over the top. What a problem. I love this one. I love this one because it just feels like it shouldn't work. It feels like, if I'm always getting 0 along the straight line, any straight line, I should be 0. So cool. So cool. All right. Well, more problems, right? More problems. So, find the following. Limit as we go to 1, 1. Okay, what is it? Well, x to the 7th y squared plus, oh my gosh, what? Sine cosine y plus y squared x plus x e to the y, and that's just the numerator. X squared plus 3 arctangent x plus y. Now, I love an arctangent problem, but my goodness. 4 secant squared of xy. Wow. What a problem. And at this point, you might be getting a little bit nervous, like, what have I gotten ourselves into? But let's look at something. See, whenever we see a limit problem, the first thing we think to ourselves is, let's just plug it in. Now, why? Well, if we have a continuous function, then we just have to plug in, and whatever the answer is, that's the answer, and we're done. Is this function continuous? Let's stare at it for a second, and let's see if it is. Well, polynomials are continuous, and that's a polynomial. Here, cosine is continuous, and there's a polynomial. Add two continuous functions, it's polynomial. Put a continuous function into a continuous function, still continuous. Exponential is continuous, x, that's polynomial. Multiply continuous functions, you get continuous functions. Add a bunch of continuous functions, you get a continuous function. Same argument as downstairs. Polynomial continuous. X plus y is continuous, plug into arctangent, so that's continuous. X times y is continuous, plug into secant squared. Secant squared is continuous, that's as long as you stay away from the asymptotes. Combine continuous functions together, you're continuous. So this is a crazy looking function, but it's a crazy looking continuous function. And that's the important thing. So, moral is, plug in 1, 1. And let's see what we get. So, we get, 1 to the 7th times 1 squared, which is 1, plus sine of cosine of 1. Well, cosine of 1, also known as, yes, that's right, cosine of 1, good. Some things don't simplify. 1 squared times 1 is 1. Then we have 1 times e to the 1, which is e. Downstairs, what do we have? Well, we get 1. 3 times arctangent of 2. And arctangent of 2 is arctangent of 2. Yeah. Well, again, doesn't have to simplify. And plus 4 secant squared. And 1 times 1 is 1. Now, the question is this an okay number? Well, we have to check a couple things. Are we dividing by 0, or is there any part blowing up? Sine and cosine never blow up. E is fine. Arctangent never blows up. And secant squared blows up, but at things like pi over 2 or 3 pi over 2. And so the odd multiples of pi over 2. And 1 is not an odd multiple of pi over 2. So that's perfectly fine. Are we dividing by 0? Well, 1 is positive. Arctangent of a positive number is positive. And if you square something, it's positive. So all your terms in the denominator are positive, which means the denominator is positive. So we're not dividing by 0. In other words, it's a crazy looking number, but it's a number. So what's our conclusion? Our conclusion is, since it's continuous, and when we plugged it in, we got an answer, that's it. We're done. We're done. This is why we love continuous functions and limits, because continuous functions with limits are so easy to do. Plug it in, and if you can get an answer that makes sense, you're done. And life is good. Well, life is always good. We're doing math after all. Life should be wonderful. All right, on to another problem. Okay, find the limit as xy goes to 0, 0, x to the fourth, divide by x squared plus y squared. Now, what's happening? Well, plug in 0, right? And, 0, 0. And we see, okay, this is going to 0 on the top, 0 on the bottom, which means more work. More work. Okay, well, that's all right. We don't mind. So we have to think about, okay, how do we do this? Now, this one is a little bit more subtle, and so I'm going to ramble for a little bit, and then sort of say, right, in some sense, think about these as polynomials. The numerator is fourth degree, x to the fourth. The denominator is like second degree, because you have x squared, y squared. So when you see that, you're like, okay, so it really says that the numerator should be going to 0 a lot faster, right? Because for a small number to the fourth, it's going to be a lot smaller than a small number squared. So intuitively, our numerator is going to 0 faster, so it feels like we should be going to 0. Now, this is hand wavy right now. You might say it's heuristic at this point. We're saying, okay, all right. Well, let's sort of see what we can do. So one of the things you can play around with is say, okay, well, let's sort of break that x to the fourth into parts. So if we did the following, we could say, let's look at it as x squared and x squared. And at this point, you're probably like, yeah, x to the fourth is x squared times x squared. And I'm going to put the x squared plus y squared under one of them. Okay, so there's our expression. And now, why do this? Well, I want to try to understand how things are changing. And here is something that we can now do. This is a little bit more subtle, and but I want to sort of say, what's our intuition here? These are roughly the same degree, right? They're both degree 2. So it should have close to a similar behavior. Now, it's not going to always be the same answer. It turns out this limit, if you covered up this x squared here, that limit by itself does not exist. But we're going to come back to it. Let's see what we can say about this. X squared over x squared plus y squared. Well, one thing for sure, everything's being squared, so it's definitely greater than or equal to 0. On the other hand, now this is the fun part. This is less than or equal to x squared plus y squared over x squared plus y squared. Now, why is that true? Well, you added a little bit. You added something positive. And so, what does that mean? Well, that means that this expression, while it may not necessarily be well behaved, it doesn't go too crazy. It's going to stay between 0 and 1. So, this piece right here is something which is bounded. All right, now that's good news. If you have something which is bounded, you're making progress. Now, we're not out of the woods yet. There's something else that needs to happen. What's the other part? Well, that's the x squared part, and let's think about that. Well, what's true about x squared? Well, what's true is that this is getting small. Whoops, I can spell small. Well, what do we mean by that? Well, as x gets close to 0, x squared gets close to 0. If you have something that's small times something which is bounded, combined, they're going to get small. So let's be more precise. We can start with this expression and multiply everything by x squared, and we'd have 0 less than or equal to x to the fourth over x squared plus y squared less than or equal to x squared. Now we're ready. We're ready for the punchline. What happens? Well, this part, as we get close to the origin, goes to 0. This part, as we get close to the origin, goes to 0. And this has to go to something in between. well, there's not a lot of space left. There's not a lot of wiggle room between 0 and 0. And so we can say by the squeeze, some people, by the way, call this the sandwich theorem. If you're really cute, you can say, ooh, squish, 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 squish. But by squeeze, we can conclude our limit as our function goes to 0, 0 of x to the fourth over x squared plus y squared is indeed equal to 0. The key argument is to show it's bounded between two things which are well behaved. Okay, and this one is truly a little bit more subtle and not so obvious how you would get to it, which is why we practice. Practice, practice, practice. After a while, you see, oh, I've seen things like this before. I know what happens. No problems. No problems. All right, well, let's test ourselves, right? We have another opportunity here. So, find the limit as we go to 0, 0 again. But now, x squared sine squared of log of absolute value of x plus absolute value of y. Now, why is this getting crazy? Well, notice this piece right here is going to 0, right? Because if x goes to 0 and y goes to 0, then the size of x plus the size of y goes to 0. That's inside of a log. Well, what is that telling us? If the inside of a log is going to 0, then that expression is going to technically negative infinity. Log of 0 that's an asymptote. It's off to negative infinity. What? So what happens is as we get close to the origin, the inside piece of that sine function is going off towards minus infinity, which means that this part right here, this is oscillating infinitely often near our point 0, 0. In other words, that sine squared is just going crazy. It's going nuts near the origin. So it's out of control. If the x squared wasn't there, no limit, because there's all this oscillation. But now we say, hold on, we've seen this before. We know there's a nice little rule in our back pocket that we can reach in and grab that says, if we're dealing with sine, the sine function is bounded. And so in particular, we can say, look, it might be oscillating infinitely often, but it's not wildly oscillating. It's somewhat controlled. So in particular, we can say, look, sine squared of log absolute value of x plus absolute value of y is in between 0 and 1. Multiply everything by x squared, and lo and behold, 0 less than or equal to x squared sine squared log of absolute value of x plus absolute value of y less than or equal to x squared. And now we do what we did before. The 0 and x squared go to 0, and therefore the thing in the middle also goes to 0. So by squeeze, we are good to go. Now, some notes. I will say we've been really lucky with these problems in that they gave us things like x squared. What if they'd given us x? Would we still be able to do it? And the answer is, well, yes, but then you have to be a little bit careful to pay attention to the sign, and you'd still be able to make it work. But just, be careful. Practice, and pay attention to the signs. Sometimes you might have to say, well, you see, what can happen with x is you might be multiplying by a negative, so that's why you have to be a little bit careful. So I guess I'll demonstrate here in a second. Here after we finish, that equals 0. Okay, we're done. If this had been x times the sine squared of log absolute value of x, log of y. So suppose this had been x instead of x squared. What would we have done? Well, we could still start with this expression, and then we say, I can't, strictly speaking, multiply by x. But what would be true is if we had this expression, x sine squared log of absolute value of x plus absolute value of y, what we could conclude is that we can squeeze it in between two things, and namely you say pay attention to the size, but just make sure you get the signs working. So less than or equal to absolute value of x greater than or equal to negative absolute value of x. You wouldn't want to put x and negative x there because you run into difficulties. Well, what if x had been negative to begin with? That's why it gets more subtle. And so they were nice when they wrote the problem and said, hey, we'll throw some x squareds in there just so you don't have to pay attention, because after all, we like you. Isn't that true? Don't all calculus teachers like their students? I think it is. I think it is. All right, I think we have time for one more. And this should be a good one. All right. Consider the following function. X squared plus y squared divided by 2x. And that's if we're not 0. And then we're going to be 0 if we are 0. So, part A, sketch and label the level curves for the function for the values or the heights of -1 and 2. Okay, that doesn't seem to have much to do with limits. Oh, part B does. Okay, determine whether the limit as we go to 0, 0 exists. And if so, give its value. If not, explain briefly why the limit does not exist. All right, let's do part A first. So what happens here? Well, the way we do level curves is we set our function equal to the heights, right? So for example, at -1, so we can think of this as, say, a height. Sometimes we write k equals -1, value equals -1. Really, that's saying set your function equal to -1. Well, certainly 0 doesn't equal to -1. So you'd have x squared plus y squared over 2x equal -1. And what would that be? Well, that'd be x squared plus y squared equals -2x, which would be x squared plus 2x plus y squared equals 0. Now you might say, you left a kind of a suspicious gap there, Steve. I did leave a suspicious gap. I wonder why. Well, because I see x squared and y squared, I'm thinking circle, so I'm thinking complete the squares. So I'm going to add 1 to those locations, because now, perfect. This will be x plus 1 squared plus y squared equals 1. So, what does this look like? Well, if we sketch, we'll get the following. We come here and we see, all right, this has a center at -1, 0, radius of 1. So the picture would be, let's see, if this is at -1, 0, let's say here's -1, it would look like this. Except, of course, we don't include the origin. Now you might say, wait, why not? Well, because when x equals 0, right, that's the y-axis, that includes the origin. All right, so we're going to label this -1. Okay, good. Well, let's do our other level curve, because I said there's, look, 2 level curves. Okay, so level curve number 2. So that's our height, k equals 2. So we get x squared plus y squared over 2x equals 2. So we follow the process. X squared plus y squared equals 4x. Clear our denominator and rearrange. X squared minus 4x plus y squared equals 0. So, okay, what do we need to add? Well, to complete the square here, add 4. Add 4 there. So this becomes x minus 2 squared plus y squared equals 4, which I'll write as 2 squared. So the center is at 2. So let's see, 2, there's her center. Radius 2. So it would look something like that. But again, not including the origin. Okay, so there we go. There's our level curves. It's a big circle and a little circle right next to each other. How adorable. Okay, great. Part A is done. Now, Part B. Determine whether the limit exists. And if it does, give a value. And if not, explain why. Well, it sounds like we have to do more work. But here's the thing. It's kind of this cool idea where if you have problems with parts A and B, then parts A and B might be connected to one another. In other words, they're not completely independent. So let's think about, can we use part A to answer part B? So what do we have? Well, what we have is we have level curves. So if you think about the level curve here, what does it mean? It means that as long as you travel on this circle here, the value of the function is always negative 1. If you travel on this circle here, the value of the function is always 2. In other words, if you were to sort of look at the picture of the function above the curves, this always has a height 2 here. This one always has a height negative 1 there. Notice that we can move along the curve here. So if I travel along this curve, this circle, towards the origin, what should I think the answer is? Well, as I travel along the curve, it's like, well, the function is negative 1, negative 1, negative 1, negative 1, negative 1, negative 1. I'm thinking, well, gosh, it's got to be negative 1. What if I travel along this circle? I get 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2. So as I travel on this circle, I get always 2. And so I think the limit should be 2. So, wait a second, negative 1 and 2 are not the same. It's a true fact. Negative 1 and 2 actually differ by a couple. So we can say the limit as xy goes to 0, 0 of f of xy does not exist because traveling on the circles from part A will give different values as well. This is being very dramatic. Like, ooh, what is he going to say next? As we approach 0, 0. So in other words, we say, look, the way we show limits don't exist, the easy way to show limits don't exist, is to say we're getting an inconsistent answer. In other words, as we approach in 2 different ways, we get 2 different values. And here, we say, look, as we approach in 2 different ways, we will get 2 different values coming out. And this is another case where it really helps to say, hey, if you just test straight lines, you're going to get a different answer than if you think about, well, wait a second, maybe I should be coming in at a more curved type way. So it's good to keep that in mind. All right, well, that's it. What an interesting idea. It combines together sort of some ideas from a previous session where we talked about level curves. And it helps to remember what a level curve is. It says that when I'm above a level curve, that says the value of the function upstairs is always fixed height. So if you're thinking about hiking on a mountain, it's like you're not hiking uphill, you're not hiking downhill, you're sort of like walking around a hill at a fixed elevation. So that as we move along the curve, we're always negative 1. As we move along that curve, we're always 2. And because they overlap, where they overlap, problem. We're thinking that we should have 2 different values. Impossible. impossible. Wow. Great way to end our session. Thank you for coming and for practicing with limits. It's a fun topic, and I'll tell you, honestly, it's one that you need to do practice on to get good at. So I hope you do enough practice. Take care, and I'll hope to see you again soon.